as a way of just starting out, I'm going to be actually going over some of the same ground that Jeff did earlier, although with a little bit of a different bent. So um, don't be surprised about that. And as a quick disclaimer, there are a number of people here who are much more qualified on the technical details I'm going to present. So if that's you, please do jump in and correct me if I don't get anything quite right. That said, let's get started. So those of you who have played pseudonaut puzzles on Eterna are probably familiar with this image here, showing the lack of our trusty energy numbers. And you're probably lamenting the loss of this really invaluable tool for making progress when solving puzzles, particularly the more tricky ones. And I've already talked a bit in the past in town halls and forum posts about why, but I'm going to go a little bit deeper into what's going on here, why we're probably going to see this more and more going forward, and why it might actually be a good thing. So we're going to talk about a few different things. First off, some high-level discussion about how our folding engines work under the hood and how we're moving beyond just looking at free energy, how we can reframe our approach to solving puzzles under this new paradigm, and finally, how we can evolve the ways we visualize RNA to match that. So first up, a refresher on thermodynamics that is hopefully accessible to the mere human, like I'd like to claim myself to be. And if you're interested in this topic, I do recommend taking a look at Nando's eternacon talk from 2016, which is on Eterna's YouTube channel, as well as this additional lecture that he recorded and posted on the Eterna wiki. Not directly related to what I'm going to talk about, but just as far as inner workings of the energy model and some interesting learnings that we can take from it. I found these to be very interesting and reframed some things just as I was putting together this talk. Now, when we talk about free energy, what do we mean by that? We have this magical number that somehow going more in the negative is better. Okay, but what does this mean? One way of looking at it is how much energy is required for something to happen, with the familiar metaphor of magnets. When you have two magnets with the same polarity pointing to each other, like two, this north polarity. If you've ever played with magnets before, right, that winds up being kind of hard to do. You get a bunch of resistance. They're actively trying to not be together. But if you flip them around, not only do they naturally want to come together, but if you, I don't know, took two weights on the end of the magnets, they'll actually move those weights. They're exerting force, and they are, instead of needing energy to be put into the system of two magnets to get them to do something, you actually have energy leaving the system. And through scientific experiments, we have measurements of the energy involved in forming different RNA structures. So, when you have cross GU pairs, remember that GU superboost, or you have a CG next to an AU pair in a stack, or a GC next to a tetraloop with a G boosting it, right? We know how much energy is being exerted or how much energy you have to put in to make these structures. And those are the numbers that you see in Eterna, which are conventionally called nearest neighbor free energies. And if you have a positive number, that means energy is required, and negative energy, or the negative number, means that the RNA is actively working to form that shape. And this is the foundation of thermodynamic models like Vienna or NUPAC, which is what Eterna originally started with. Now, this is all fine and good, but how do we actually get predicted structures out of that? And that's actually a pretty difficult task for our models. They actually wind up going and looking through all possible different pairs the RNA can make, all the different possible structures for this given sequence, and it calculates the energy so for each individual structure, it will go through and calculate the energy of each kind of substructure, so each loop or quad, so two stacks together, and it'll sum up all the substructure energies, all the nearest neighbor free energies in that structure, and it will compare it for all of these different possible structures in a bit of a smart way, using some fancy dynamic programming tricks in the actual algorithms themselves to make it more efficient. But it winds up trying to figure out what is the structure with the lowest total free energy, which we call the minimum free energy structure. And that's what you wind up seeing in natural mode. And all of these different possible structures together we call the ensemble. And when an RNA is actually synthesized, there will be multiple copies of that same sequence. in the experiment and even in nature. When you have different copies of the same sequence, they're not always going to be folding into the same structure, and they'll be even changing between them over time. And that's where we take a quick diversion into statistical mechanics. And don't worry, this isn't going to be on the test. There's not going to be a test, but anyways, as it turns out, the probability of forming a particular secondary structure is correlated to its free energy. And this is what's particularly correlated in what's called a Boltzmann probability distribution. So this actually reflects the underlying chemistry, where the electrons are hanging out on the atoms in these molecules. Why do the RNAs behave this way? It's because that's how the chemistry behaves. And the top equation here is called the partition function, which you may have heard that term before. And what we do is we sum what's called the Boltzmann factor, this bit on the right, which is derived from the free energy and the temperature. Specifically, you have Euler's number raised to the power of the negative free energy divided by the Boltzmann constant times the temperature. And so we sum that over all the different possible structures, and that's what's called the partition function. And then we can use that in this bottom equation to say, hey, if we have a particular structure, we can take the Boltzmann factor of that structure and compare it to the output of the partition function, so all the structures, and then that's going to be the probability that that structure shows up, right? And when we talked about the entire ensemble of structures, not only is this useful when we're actually looking at predictions from algorithms saying, oh, well, it's more or less likely to show up. This is actually, when you're actually synthesizing them, this is the percentage of time a given sequence or a given structure will wind up, it's the percentage of time one of this sequence that we're looking at will fold into the particular structure that we're looking at. Or when you have a bunch of different copies, the percentage that are going to be folding into these different structures. So to oversimplify this a little bit, the free energy of a given sequence, or of a given structure for a sequence, compared to the total free energy looking at all different possible structures, gives you the structure, the possibility of that structure occurring. And this winds up giving rise to a lot of different interesting properties in RNA switches and RNA kinetics, but that's beyond the scope that we're talking about here. And also, this is where our dot plot comes from. What is the probability that two different bases will pair, given the probabilities of all the different possible substructures? So looking at all the when we're talking about this pair here, right, and what percentage, so out of all the different possible structures, which ones include this base pair? And then when we sum up the probability of all those different structures, what winds up being the probability that, it's going to be one of those. Now, that being said, we have a new kid on the block, which is machine learning based models, as Riju was talking a bit about before. You've probably heard the terms machine learning and artificial intelligence thrown around a lot lately, but it winds up being quite useful. Now, it's a little bit magic with a bit of statistics and a lot of data. Computers can determine complex relationships that would be really hard to come up with just by hand. And it's not foolproof, and it takes a lot of work to come up with something that's not completely meaningless, but it winds up being done well. It provides a really powerful tool that we can use. Models like Eternafold and Contrafold, which is based on, wind up using this approach. And instead of measuring the parameters for different types of pairs or different loop sizes, we take some known structures, right, where we know what it should roughly fold up to when synthesized, because we've done those experiments, and then takes those sequences, comes up with the ensemble of structures, and then says, hey, we have all these parameters, and we want to just come up with the values of those parameters such that no matter what sequence we throw into it, that the correct structure always comes out on top. And because of the Boltzmann distribution that we saw before, we can actually use that in reverse. So so the output of models like contrafold and eternafold wind up being probabilities, and we can take those probabilities and go back to free energies. So then what's with the free energy not being available? Well, first off, bugs, and this is in particular with NUPAC. Energy calculation is straight up broken in a number of different ways. In the best case, the results are completely bogus. In the worst case, it crashes, specifically with pseudonauts. If we ignore pseudonauts for a minute, the eternafold energy calculation, you might actually have noticed that it's not quite right. There are some situations where the minimum free energy structure has a higher energy than the target structure, which shouldn't be possible. As far as I can tell, that's due to some sort of bug in the way that the energies are calculated from the probabilities, or maybe a difference in the ways that the different parameters work. I'm not entirely sure. But then when we look at our Threshnot-based predictions for pseudonauts, it winds up being a little bit more interesting because Threshnot doesn't use free energy in the same way that these other models do, even in the way that eternafold and contrafold do. And the natural mode, it's not a minimum free energy structure at all. So what Threshnot does is it takes those phase pairing probabilities that we saw before, and in the case of eternafold Threshnot, they're actually the probabilities coming from eternafold, not even taking into account pseudonauted structures. And Threshnot comes up with a structure saying, as long as, so when we look at a given pair, as long as it's greater than some cutoff, and we wind up using 0.15, as long as the probability is greater than that cutoff, and it's the most likely pair for both of the bases involved. So in this case, both the highest value for both the row and the column, then we'll use that as part of our structure. And that means that the structure that we wind up getting out of it might not be the one with the lowest energy. We don't even have calculations. We don't have numbers for these structures that are involved in pseudonauts. So when we know how to come up with energy numbers from eternafold, or through eternafold, we can come up with them for non-pseudonauted structures, but we don't, when it's forming these pseudonauted regions, we don't actually have those numbers in the first place. And also, the default behavior for eternafold, which we don't use, is actually kind of winds up being, even without taking pseudonauts into account, winds up doing something similar to the Threshnot algorithm. And it provides what's called instead of a minimum free energy structure, it provides a maximum expected accuracy structure. So we choose some pairs or lack of pairs based off of whatever makes the probability across all the bases and pairs on the entire structure the highest, instead of whatever makes the probability of the structure itself the highest. And again, this might not be the minimum free energy structure. And this approach has wound up being more accurate. So going back to this, we don't have energies in some cases because the energy is broken. In some cases, because we're coming up with calculations that we don't have the data. And at the very least, when you're looking at the delta is going to be meaningless anyways if we're using a way of getting a structure that is not related to finding the structure with the lowest energy. Back to machine learning, we're seeing some newer methods that may not even be based around the likelihood of computing probabilities or energies for substructures in a way that we can turn it back into an energy at all. And it might use some more opaque calculations. So for example, we might take some strategies from text and image processing, doing something like taking overlapping sequence regions and throwing them through multiple layers of calculations that wind up getting combined together. And we need to find a way to work with, be able to solve puzzles when we don't have that trusted tool of energy and the energy delta. But at least so far, the tools that are being developed, we can still have some form of base pairing probabilities. And as it turns out, the way that we currently approach puzzle solving, trying to come up with a minimum free energy structure, it's actually pretty complicated and non-intuitive. I like to describe the current situation as an adversarial Sudoku. So imagine instead of needing a 0 to 9 in every box, row, and column, as a normal Sudoku, you need to come up with a set of numbers where you plug them in a particular order. You take that and you put it into a massive chart of formulas. You get a number, and you can't have an arrangement of those numbers that you chose such that there is an entry in the chart that adds up to an even lower number, or that winds up being a lower number. And by the way, we have multiple sets of these magic formulas, and none of them are easily accessible for you to figure out what they are. And if you ask me, that's pretty bonkers. I think Eterna players are insane for being able to do as well as they have. And it's no wonder that new players get really confused when they're going and solving puzzles. And they say, like, why did this whole puzzle blow up when I just made one small change to this area over here? Well, because what you're doing is not actually just changing the behavior of the target structure. It's not just, well, I flipped this pair, so the target structure behaves differently. You're actually changing all this entire ensemble of structures, which we don't really surface anywhere. But maybe it's better to, instead of Sudoku, maybe it's better to compare this to, I'm not sure if anybody's seen this thing that's been making around, it's making its rounds, and there's a Steam game, 5D chess with multiverse time travel. So maybe it's not quite this bad. But instead of our typical approaches of getting the energy delta down to 0 and relying on subsections and branches of an RNA staying intact when we make changes to one region, when it's not causing interactions with some other regions, what if we looked back at the dot plot, which is kind of an easily overlooked tool, but it's proven really important in success in the lab. And if we focus more on this instead of the energies, I think this actually gets us closer to what our goal has been the entire time in puzzle solving, and especially doing well in the lab, which is increasing the likelihood of our target structure when we compare it to the entire ensemble. And we actually get a few benefits here. So first off, we get a continuous scale of improvement rather than just solved it or not. As you're solving a puzzle and you haven't gotten the predicted structure to match, you have an idea of progress. I mean, you kind of get that with the delta, but you have a better idea of, I'm getting closer to getting this structure correct, and especially on, at the level of individual bases. And then even after you have matched the one predicted structure, you can even work on improving it further to get it more and more likely that it's going to work correctly. Additionally, this means there's a higher visibility into the ensemble, which means more insight for players into how the RNA actually operates. Plus, also, I think it winds up being a better intuition when you're solving puzzles. Instead of, as I said before, instead of flipping pairs and magically the structure solves, you can directly see how the changes that you make are impacting the outcome by seeing how you're changing the likelihood of interacting with different bases across the entire RNA. But we have one more thing to deal with, which is, how do we visualize this information? The dot plot is not exactly the most intuitive. One option could be taking the example provided by J. Nicol with his dot plot puzzles, using and actually coloring the individual bases based on their probability of being correct. Or maybe J. Anderson Lee's arc plot booster, which we saw before, which is, one way that you can do it is just basically like the dot plot, but also these arcs and the rings give you a better intuition for how individual bases are kind of connecting to each other. It's a bit less abstract. Maybe we could also do something that's a little bit more dynamic and something that you can play around with a little bit more. Let's take the idea of the arc knot, or the arc plot, and actually overlay it directly on our existing 2D representation. You don't want to see all the lines all the time, or else you're not going to be able to actually see anything. But what if you said, hey, just show me the probabilities of different interactions with just one base, or show me all of the probabilities above a certain likelihood or below a certain likelihood. Or maybe what are the possible pairings across in, when you're looking at an entire stem, for example. Or maybe we get a little even more abstract and we say, hey, let's look at our RNA not as individual bases and pairs, but as higher stems and loops and say, hey, when we're looking at the target structure, what's the probability of this entire stem? And what other, is it having issues internally, or is it potentially interacting with some other larger region of the RNA? And then you can collapse, instead of having all these arcs going all over the place, you kind of collapse that information down a little bit more. And you can zoom into and work on individual sectors at a smaller level. Maybe there's a way we can start exposing more of the individual suboptimal structures than what you see in the actual mode. Or maybe it's something that no one has thought of yet. And I think there's a lot of potential. It's an area that we haven't really, I don't think, thought too much about. And I think there's a lot we could potentially do. Point being, we have a challenging problem at hand, but I think we also have some powerful tools at our disposal, and some the chance to explore some exciting ideas. And maybe we can take our 5D chess and turn it into something a little bit more manageable. Thanks.